Hello, I'm Diego from Revision Dojo and welcome to the second video on A.1 Kinematics. This video will focus on projectile motion. We have already seen the entirety of A.1.1 and right now we're going to focus on A.1.2. Alright, there is only one learning objective for this session, so just write this down and make sure that at the end of the lesson you understand what it says. First, let's start with a very quick assumptions section. Here in projectile motion and in general in IB physics, we assume that there is a constant acceleration acting on all bodies close to the surface of the Earth. The Earth is actually not perfectly round. It's a little bit flatter at the poles, so it looks a little bit more like this if we really exaggerate it. So gravity is not actually even everywhere on Earth, but we ignore that in IB physics. Furthermore, we assume that the surface of the Earth is large enough that at any point it is considered flat. So when we're looking at a projectile motion problem, we're assuming that the surface of the Earth, so the ground, is always flat. Alright, let's move on. So 2D projectile motion, which is the only projectile motion we care about in IB physics, there are a couple typical situations in projectile motion. First, an item flying straight up, which is something we saw in one of the sample questions in the previous unit, and also an object going at an angle. This is what we call ballistic motion, and essentially the object is going to have a trajectory approximately like this. It's very important that we also consider that most of the time we will ignore air resistance when we're talking about projectile motion. Let's take a look at a couple sketches of what projectile motion graphs look like. In projectile motion, a displacement time graph would look something like this if the object is thrown upwards. The object goes up, away from its starting position. This is the point where it is the farthest, and then it comes back down. Alright, so this is for displacement time graphs for when you throw an object straight up. However, the distance time graph is going to look completely different because it's going to look a little bit more like this. Indeed, distance is the sum of the length of the path taken. That means that here is the maximum height point. So the object slows down as it reaches its maximum height and then accelerates once again as it comes down. Now we need to calculate the motion in both vertical and horizontal planes. Gravity only acts on the vertical plane. So most of the time you're mostly going to care about the vertical plane because we are ignoring air resistance. So horizontal motion most of the time will have an acceleration of 0. An important thing about horizontal motion is you can calculate the horizontal distance traveled. So if you're firing an object out of, for example, let's say a cannon here, and you want to know how far it traveled, you have to do horizontal velocity times the time it took to land. Now, you might ask, how do we find out the horizontal velocity? Well, this is where vectors and scalars come back. So let's assume we have a ball that we throw at a certain angle, which we're going to say is a 45-degree angle. We throw this ball with a velocity of 10 meters per second. And here we want to know what is the vertical and what's the horizontal motion. Well, what we do is we use trigonometry. Because any vector quantity, and velocity is a vector quantity, can be split into its vertical and horizontal components. Let's assume this red arrow is our velocity vector. We can find its vertical component and its horizontal component using trigonometry. Luckily, we have this 45-degree angle to help us out to find the components. We're going to call this horizontal component VH and the vertical component VV. Using trigonometry, we can find VH by using cos of 45 degrees equals VH over 10, because VH is the adjacent there and 10 is a hypotenuse. Here, because we're using 45 degrees, the vertical and horizontal components are going to be equal, because 45 is exactly half of 90. So the angle here is also going to be 45 degrees. However, in questions, it doesn't tend to be the case, and you have to use cos of a different angle for the other component. Let's do the math. So 10 times cos 45 equals 5 square root 2, which is approximately 7.07 meters per second. All right, that's how you break down velocity into its components. Let's see some other quick facts about projectile motion. If your motion is in a bell trajectory, your highest point is going to be at the middle, and it's going to act as an axis of symmetry for the motion. So there's going to be the same horizontal distance between the point of max height and the beginning of the motion, and the point of max height and the end of the motion. These are going to be equal. It's the same for time. The time taken to the point of max height is half of the time for the total motion. Keep those facts in mind, they will really help you to solve projectile motion questions. Alright, that is nearly it. We just need to quickly talk about vertical motion a little bit more. Your vertical velocity is the most important factor in your projectile motion because your vertical velocity is the only one that has an acceleration. So your VV is going to decrease until the point of max height. At the point of max height, and this is important, so at t, VV equals 0 because it's just about to start moving downwards and it has finished its upwards motion. This is important because it can help you find that point of max height. Then also remember that there's always a minus 9.1 acceleration downwards. It's negative because it's acting against your vertical velocity, so you must keep that in mind. Also, your VV is going to be negative. It's going to be smaller than 0 in the second half of the motion, so after t. Big T is the time to maximum height. Alright, I don't want to complicate projectile motion more for you because it is actually a relatively simple concept if you manage to understand all of those little facts. Alright, let's take a look at our sample question to finish off this lesson. A student strikes a tennis ball at point P. The ball is initially directed at an angle of 7 degrees to the horizontal. Calculate the time it takes for the ball to reach the net. Alright, let's highlight some important information. So we're looking for time, we have an angle of 7 degrees, and we start at point P. We have a beautiful diagram here. And like any projectile motion question, let's start by finding the components of this velocity vector right here. So our horizontal and vertical velocities. To do so, we simply use the formulas we used before. So here we need cos 7 for our horizontal velocity, and then we need cos of 90 minus 7 for our vertical velocity. So let's find out. All right. Here, make sure to always keep your answers unrounded. If you round them, your final answer might be wrong. So we have our vertical and horizontal velocities. Now what we're looking for is the time it takes for the ball to reach the net. The easiest way to do this is simply using horizontal velocity because we know how far we are from the net. We know our horizontal velocity, and we know that our horizontal velocity is not affected by any acceleration. So it's actually as straightforward as doing this divided by our horizontal velocity. Don't forget the seconds at the end, and that's it. It's very quick, very straightforward, easy question. Always start with splitting the components. Then you'll be able to answer any question much more easily. Alright, that's it for projectile motion. I hope you understood everything. Otherwise, please drop us a comment for the rest of A.1, which is movement through fluids.